We want the value that appears more than half the time in the list. In 2, 2, 1, 2, 3, 2, 2, there are 7 elements and the 2 shows up 5 times, well over half. Counting each value works, but Moore's voting finds the majority in one pass using just a single counter. Picture an election where each element votes. We hold one candidate and a count of its lead. When we see the candidate again, its lead grows. When we see a different value, one vote is canceled, shrinking the lead. If the lead ever drops to 0, we adopt whatever we are looking at as the new candidate. Because the majority value appears more than half the time, its votes can never all be canceled, so it survives as the final candidate. We begin with the first element as a placeholder candidate and a count of 0. For each value, if the count has fallen to 0, we adopt this value as the candidate. Then, if the value matches the candidate, we add a vote, otherwise we cancel one. The value left standing is the majority. Let's build Moore's voting and find the majority. We start with a placeholder candidate and a vote count of 0. Whenever the lead has been canceled down to 0, we adopt the current value as the new candidate. A matching value adds a vote. A different one cancels a vote, and the survivor is the majority. Now, let's test it and hit run. The 2 wins the first list, appearing more than half the time. 4 wins the second, and 7 trivially wins a list that is all 7s. For each item, if the lead is 0, we adopt it as candidate. Then a match adds a vote, and a mismatch cancels one. The majority value cannot be fully canceled, so it remains the final candidate. We make one pass with constant work per element, so order n time, and we keep only a candidate and a counter, so order 1 space. Moore's voting assumes a strict majority actually exists, so if you are not certain, do a quick second pass to confirm the candidate really appears more than half the time. Only switch candidates when the count reaches 0, and remember majority means strictly more than half.